Hi, welcome to the second video, the voltage source inverter simulations using PLECS. In the previous tutorial, we saw how to implement the control and the pulse width modulation in the Simulink environment, and in the PLECS environment, we hit the power circuit of the inverter. The target of today's tutorial is to see the harmonic analysis of the converter system. So here you can see we had implemented the pulse width modulation. In this case, it was a sinusoidal pulse width modulation. So inside the block of sine, we have three phases of sines here implemented with a phase shift of minus 120 degrees and minus 240 degrees respectively for phase 2 and 3. For the triangular one, which we have taken as a carrier wave, we defined the pattern to be so here, and the relevant variables as input in the block are then defined in the MATLAB script here to the left. And inside the block environment of PLECS, we have the circuit. You see, it is a three-phase IGBT-based inverter for two-level operation, and here we have the DC link implemented using a constant DC voltage source. On the load side, I have considered NRL load. The values of hose are then implemented here in the M file. The resistor part is taken to be 1 ohms and the inductance part is taken to be 1 millihenries. I have taken two signals, the current of the line and also the voltage of VAO, the phase voltage. I apologize, the voltage VAB to the Simulink environment so that I can export them to the MATLAB workspace and analyze them using the FFT. This is the target, so to speak. So I take VAB, which is the voltage between phase A and B, and we take the current from here. So there are a couple of ways to analyze the frequency spectrum. One would be if we just simply run the simulation and take a PLECS scope here in the Simulink environment. We can double click here and it will take some time. I will come back when the simulation is finished. So the simulation is now complete. As you can see, this is the line current of the inverter output side. One way to implement the FFT is to use the inbuilt property from the PLECS. If you go to here on the Fourier spectrum, you can see, and if we click here, then a second window pops up. And this value shows the results for the two cursor positions here. Let me maximize the curve. What is the target for our case? And it is to analyze the spectrum for our base frequency, which is 50 Hertz. And let's analyze it for a range of 5 periods. We click OK. You can see at 50 Hertz, we have the fundamental component of the wave of current. Now you see there's some parts missing here. But before that, let me show you how the typical frequency spectrum would look like for this type of converter. So this is the frequency spectrum shown for this two-level voltage source inverter. So on the top window, you see it's a VAB, which is the line-to-line voltage, which is also taken for our analysis. And then to the lower plot, you can see the frequency spectrum. If you notice carefully, the horizontal axis is representing the order of harmonic. So in this case, really, even though it is simulated for 60 Hertz frequency, it doesn't really matter. We will also see it for our 50 Hertz frequency, and the order of harmonics will be plotted. And if you notice carefully that the fundamental component is 0.49 times the DC voltage level. And this particular case is simulated for an amplitude modulation of 0.8 and the frequency modulation is 15 times the fundamental frequency. In this case, we will have the harmonics at MF plus minus 2, 2MF plus minus 1, 3MF plus minus 2, and so on. So to see the relevant frequency contents in here, we need to increase the number of harmonic here, which let's take for 100th order. So now it's clear that we have for fundamental components, and we also have for MF plus minus 2. But since it is not very handy to analyze at what exactly the harmonics order, we cannot do much of the analysis here. That's why it's a good idea to export the curves and then analyze it in an external script so that we have more control of the results. To do that, let's now export the curves. I will do it for voltages here. So for that, we will take two files. It's connected here. Let's give it a name. I'll call it the line to line voltage, and let's the variable to be VAB. And I'll save the format as the time series. The decimation, let's take it 2, and the sampling time is also important. I will take the simulation sampling time, which is then T max step. Now the accuracy of the calculation are going to be determined using this time step. If you have a lower resolution, the results are not going to be much accurate or in the acceptable range. For that, I have taken 1 microseconds of time step, which should be good enough. And that is one of the reasons why the simulation is running too slow as well. I will run the simulations again and come back after it's finished. So again, the simulation is now complete, and let's analyze the Fourier analysis again. So here you see this is the voltage between the phase A and B. And if we take again for comparison purpose, and again the FFT of the signal, I want to specify the base frequency to 50, and let's analyze it for 5 periods. And as I mentioned, the order of harmonic then should be increased to 100 so that we can have all the major harmonics available. So you can see for the fundamental component, we have a peak value of around 550 volts. The second major harmonic would be then at MF plus minus 2. That means our MF was at MF. Let's see what the value of MF was. So MF is 15. Let's check again here. For 15 plus minus 2, so it should be around 13. So the order of harmonic should be around 13, and 13 times 50 is then 650. So if we check the second major one, this should be a 650 Hertz harmonic, which is here. So 152 is the peak value. If we use the PLECS inbuilt FFT analysis, they will always give you the peak value of the voltage or current, or in general, the relevant variable. It shows the peak value of the FFT. Now, if we go back to this MATLAB environment, here I have written a script to calculate the FFT, the same that we did for the signal here using the PLECS environment, but here we have more control of the signal. Using these two files, I have saved the time series under the variable now VAB, and then it should be available in our workspace. As you can see here, it keeps going. So you can see the variable is available LLV format. And if we open it, LLV, then in workspace, the variable should be VAB. Where is it? See on top here, sorry, on the bottom right corner, we have the VAB variable. So we can import the variable again to this script and proceed with the further calculation. First, I would take the time, which is shown here, and then another variable. I take it is from another calculation. I just left it as it is now. So IRST is principally the voltage of the difference between two phases. If we continue, you said I have defined my fundamental frequency to be 50 Hertz, and then I specify a time range for which the FFT should be carried out. I start from 0, and since my simulation runs to the point, how long was it? It was around 2 seconds. So it should be good enough if I take 1 or 1.5 for the calculation. And then it carries on. Then I select the signal only for this given time range and carry on with the analysis. Then for the calculation of the THD, I extract the fundamental component, RMS values, and also that of the harmonic spectrum, and use the values to calculate the total harmonic distortion. This is with reference to the fundamental component, of course. And then to the bottom, I plot it into two windows in a subplot. One is containing in terms of the frequencies. That means in the horizontal axis, we have the frequency, and to understand it even better, I also take the order of the harmonic. Let's run the script and see the results. What I also considered here, alongside the peak value of the FFT, I also took the RMS value. So in the tip value at 50 Hertz is then 550 volts, which we also saw it from here. So this is now validating our calculation here. The script is now calculating exactly what the PLECS itself was doing. And to the bottom side, we have again the same value of FFT, but now in terms of the order of harmonic. So in this window, we can clearly see this is the first order, which means the fundamental. Then we have the 13th order, which represents them MF -2. If we have this one, that is MF +2, which is 17, and so on. So this here we have more control on the visualization of the data and also the calculation. For example, for the THD calculation, we have considered the RMS value here in the script, and we can also show the results here. Like if we have the THD, you can see it is 91.15% of THD, which is quite high for this case. But for the analysis purpose, maybe we need to design filters and so forth. And similarly, we can also carry out the calculation for voltage and current for other phases and for all of the relevant information that we are interested in. I think that's all for this tutorial. And one final thing to note here is that I have taken the time step for the simulation to be 1 microsecond. I have noticed that if the time is any less than this one, the calculation is not accurate enough. So it is a type of trial and error method. You have to figure it out which time step gives you the best result. And for me, if I do 1 millisecond or 0.1 milliseconds, it was not really giving the accurate result. So 1 microsecond works fine for me. For you, you also need to find the optimal value for that and specify the values, of course, in the solver settings as well. I have taken a stiff solver, and you see the maximum steps as I have taken to be 1 microsecond as well. Thank you for watching, and let me know if you have any questions or queries to know. Thank you.